Factoring is a process which breaks up or reduces a given number or algebraic expression into its parts. For example, an elementary explanation of factoring ordinary numbers may be reviewed in a tape called Numerical Fractions. The simplest application in algebra is to factor a single term expression or monomial. For example, factor 12x squared y cubed z. The factors are 2 times 2 times 3 times x times y times y times y, and finally times z. But there are more complicated applications of factorings than that example. Factoring methods will be applied to multinomials and polynomial expressions. You will discover that factoring algebraic expressions is basically a matter of memorizing techniques and recognizing the factoring types the expression belongs to. The first of the types is referred to as the common factor. Given a polynomial or multinomial, determine the factors of each term common to all. For example, 6x to the fourth y squared z minus 12x cubed y to the fifth z cubed plus 3x squared y squared z squared. Each term separately can be factored into its parts in a manner explained in the earlier example. Of the factorable parts, there exists only a selected group of them which are common to all terms. For example, one factor common to all terms is the number 3. This term contains a 3 in the number 6. Three is a factor of this term because it's a factor of 12. And of course, 3 is also a factor of the last term. Examine other parts of each term to determine whether there are any other factors in common. Notice that we have the power x to the fourth there, x to the third there, and x squared. In addition to 3, there is an x squared that's a factor common to all of them. Look for other common factors in the expression. Well, the next power is y squared. We have y squared, y to the fifth, and y squared over there. Well, y squared is certainly a factor of that expression, and also is part of y to the fifth. So y squared is also a common factor to each of them. Check z in the same way, and we can see that z alone, since there is only one factor of z there, is a common factor in all 3 parts or 3 terms of the entire expression. Let's look at that 3x squared y squared z in the following way. I'm going to write 3x squared y squared z followed by 2, since 3 times 2 is 6, x squared, since x squared times x squared is x to the fourth, This result here in red ink and black has the exact same value, or is the same meaning as this entire term. Continuing in the same way, let's look at 3x squared y squared as part of the next term. You see that what we have left over is the 4, since 3 times 4 is 12. We have an x, since x squared times x is x cubed. Y to the third, since y squared times y cubed is y to the fifth. And finally, z squared. This entire expression is exactly equal to this term. And finally, 3x squared y squared z multiplied by z is equal to this last term in the example. If you simplify this, you can see that this is z squared and everything else is the same. So those two amounts are equal to each other. Well then, the common factor that you are looking at is also referred to as the highest common factor. The highest common factor or simply often referred to as the HCF, is 3x squared y squared z. There is no other factor that you can extract that's common to those terms that we started with. Now what you want to do is to write the expression in factored form with the highest common factor outside of the expression in this fashion. This is equal to 3x squared y squared z multiplied by 2x squared minus 4xy cubed z squared plus z. Expressions containing common factors range from the simple to the complex. When algebraic expressions contain common factors, the process of simplification expects factored expressions. Here's another example, a little simpler than the one we just did. We have 6x plus 12. The common factor to both of these terms is the number 6. So 6 taken out as a common factor leaves x behind for that term and plus 2 behind for that term. Here's another example. $14y minus 7 is equal to 7 brackets 2y minus 1. Notice if you reverse the process. Another example, 4x cubed y minus 3x squared y squared is equal to x squared y out as the common factor. We will leave behind 4x within brackets there and minus 3y in brackets there. Another example, we have 7a times 3x minus 2y plus 2b times 3x minus 2y. This is a slightly more complicated problem. You will notice that we have in brackets in the first term, remember what we said regarding terms, that this is a term and this is another term, since the part in brackets is confined to a unit, that the amount within brackets is identically the same as in the one term as the amount in brackets of the second term. If we consider this as being one unit, let's say this triangle represents it, and this triangle represents that. They're both the same. Then the triangle or the binomial factor are identical, and if you take that out as a common factor, let's start with triangle as a common factor, what is left after taking that out of the term is 7a and plus 2b. Of course, what we want to say then is that 3x minus 2y is the common factor, and taking that out of the expression will leave 7a plus 2b behind. Another example, we have 2x multiplied by x minus 1 minus x minus 1. Notice we have the same kind of expression as I've just done. If you like to think of the part in brackets here as some other quantity represented by a single symbol like this square, then this square is a factor common to this term and that term. If you take the square out as the common factor, notice that we have left the 2x out of that term. And remember, as I explained above with the example here regarding 7 being the common factor, that at least you have negative 1 left over as the common factor, as the result after taking the common factor away from that term. To rewrite that with x minus 1 in place of the square, followed by 2x minus 1. Difference of squares means having a multinomial or polynomial consisting of two terms in which each term is a perfect square. For example, x squared, that's a perfect square, minus 4, that's a perfect square, and the minus sign indicates that we're subtracting, and consequently we're looking at a difference between two perfect squares, or simply squares. Again, another example, x to the 4th minus y to the 6th. Now that's an example of a difference of squares again, because x to the 4th is the square of x squared. Y to the 6th is the square of y cubed. Remember your rules of exponents to identify these as squares. Another example is 25x squared, y to the 4th, minus 1. Notice again, we have the difference, the negative sign, of squares. That's a perfect square or simply a square, and so is 1. 1 is a square. Another example, x to the 4th minus 16. Each of those are obviously squares. Now I expect you to memorize a formula to factor those examples. Each one is a difference of squares type of expression, and so the formula is a squared, the first term squared minus b squared is equal to a minus b times a plus b. A squared becomes a and a in each of the two factors. B squared becomes b and b in each of the two factors. And in between, we have the parts separated by a minus sign and a plus sign. If you reverse the order of these two factors, it won't make any difference. So, let's apply this formula to the examples shown. X squared, here are the examples, x squared minus 4 is equal to x minus, followed by x plus 2. The next example, x to the 4th minus y to the 6th is equal to x squared negative y to the 3rd followed by x squared plus y to the 3rd. Negative there and positive there. All other parts are the same. Next, we have 25 x squared y to the 4th minus 1 is equal to, for this term here, we'll put this 4 closer to the y, is 5xy squared, all of it, 5xy squared, followed by minus 1, put that in later, and then 5xy squared plus 1. There you have the factored expression for that example. The last one we have is x to the 4th minus 16. Be careful of these kinds of problems. Here is a solution that you might not have expected. X to the 4th minus 16 is equal to x squared negative 4, end of bracket, start a new bracket, x squared plus 4. Putting in the signs now, negative and positive. Really emphasizing the fact that you end up with the same term there and there as you do here and here, and only the signs in between are separated. But notice again, doesn't this part of the answer look like the given question up there? It was factored in the example, as you see, in this line. So consequently, what we are saying is that this problem has not been finished yet. X squared minus 4 can be written as x, I will ignore the color now, and write x minus 2 followed by x plus 2 followed by x squared plus 4. Don't be trapped into thinking that if we're adding squares that it can be factored. It cannot. This does not say anything about the sum of squares being factorable. Only the difference of squares are factorable. Consequently, these sum of squares can only be left and expressed as you see it. Can't go any further with it. The next type is referred to as factoring by grouping or factoring by parts. The expression is split up by using brackets so that familiar factoring methods within the expression can be identified. For example, PH plus QH plus PK plus qk. If we take the first two terms and put brackets around them, we can identify a familiar factoring type. Notice pH plus qh results in an expression with h as a common factor. Remember doing that? That was the first type of factoring that we studied. Similarly, if we bracket pk and qk, we end up with the same kind of situation. So now, this is what we mean by factoring in terms of grouping. Grouping will identify familiar factoring types within the expression. Now, let's take the common factor h out of this part, which is p plus q. Take out the common factor k from this expression and write p plus q. You can see that I am factoring this expression by doing it in parts and grouping them so that I can identify familiar factoring types within the problem. Look at this last line and notice that p plus q in this term is common to the same quantity in this other term. In other words, p plus q is a common factor. Remember doing this earlier? If I identify this as a single symbol, then the triangle is a common factor of those two terms. And so the result is triangle times h plus k. In other words, it is p plus q, the common factor taken out of each of the terms, leaving h plus k behind. In another example, we have 3x squared plus 6x minus 2x minus 4. Group them in a way in which familiar factoring methods can be identified, and this is possible if we take 3x squared plus 6x, lumping those two together, taking 2x minus 4, putting the minus sign following by the bracket. Be very careful. 4, I had better put a plus 4, not a minus 4, for the rest of it. Each of these parts have common factors, namely, if I take 3x out of there, I end up with x plus 2, and if I take 2 out of there, I end up with x plus 2 again. Notice that this line, with its parts identified, will show that x plus 2 is a common factor in both terms. So taking that out as a common factor and putting the remaining factors within the second bracket, we write 3x minus 2. The next factoring type is factoring a three-term polynomial or a trinomial.